Thanks everyone for coming. So my name is Jebin James, and I'll be giving you an overview into what it means to choose catalyst for ammonia cracking technology. But first, I'll start a little bit of an introduction to my company, Duiker, where we come from, where we're going. Then talk a little bit more about the ammonia cracking technology itself before diving into the details of the choice that happens when you want to choose a catalyst. So in terms of a company, Duiker is a process technology solutions provider based out of the Netherlands. What makes it special is, as far as we know, we are the only company in the world that have successfully combusted 100% ammonia at industrial scale with very low NOx emissions. And when I say very low NOx emissions, I mean between 50 to 80 ppm of NOx at 3% oxygen, and that's pure ammonia. This started in about 2009, so we've been doing that for 15 years already. But more recently, we took this knowledge and know-how and developed two technologies based around this. The first is ammonia cracking, so the conversion of ammonia to hydrogen. And the second is ammonia fuel boilers. So that's making high-pressure steam from ammonia. As an organization, we have three core technology areas. The first is focusing on sulfur solutions, which is essentially our legacy business, where we actually started developing ammonia combustion. The second is clean technologies or clean energy. That's focused more on ammonia to hydrogen and ammonia to heat value proposition. And the third is reducing emissions. So this is where we work with companies like Duiker. We have a partnership with them to help our clients decarbonize their combustion systems. But this presentation, of course, I'll be focusing mainly on the ammonia to hydrogen section. Now, why ammonia? Well, we're talking about hydrogen. I think many of you are already aware that ammonia is being used or being promoted as a hydrogen carrier. And just to see how good your knowledge is, I'm going to do a quick quiz. So as you know, we transport and use ammonia globally. So we produce about 20 million tons of ammonia and we trade it globally. So the question is, what is the hydrogen equivalent of this transportation? If you think it's about 1 million tons of hydrogen this was equivalent to, put your hand up. No? If it's about 3 million tons, put your hand up. Okay, 2. And then if it's about 10 million tons or more, put your hand up. Okay? Well, actually, you're quite on the money there, gentlemen. So it's about 2.8 million tons of hydrogen. So the reason it's being considered is because it is something that's already carrying hydrogen, and we're already transporting 2.8 million tons of hydrogen equivalent. So when you want to meet EU's ambitious goals of 10 million tons of hydrogen import, you've already got a head start. So why not take advantage of this? So in making this ammonia cracking, or let's say ammonia to hydrogen value chain happen, the missing piece is, of course, ammonia cracking. And so that's where Duiker has used our knowledge to develop an ammonia cracking system. It's commercially available. And because we can use the ammonia itself as fuel, there is no CO2 emissions. We can produce extremely low NOx emissions. And that's important when you're looking to decarbonize. You have to also consider other environmental impacts. And we are the only technology supplier who can deliver the hydrogen at 50 bar directly. And this also has a consequence for the footprint. And it also is a system that can be scaled up. So we can go from 275 tons per day of hydrogen to much higher scales. But now, of course, there's the question of the catalyst, right? So we are here to talk about the catalyst. Why would you pick nickel versus ruthenium? Well, there are two catalysts with different characteristics. Nickel, for example, typically is operated at higher temperatures, whereas ruthenium could go to lower temperatures. Of course, temperature is one part of the equation. There's also the price element. Nickel is one of the most abundant metals on the planet and costs about $18 per kilogram, while ruthenium is a little bit more expensive than that, at $18,000 per kilogram. But what would be the flip side for using ruthenium? And that would be coming from the CAPEX side. Now, if you have a high temperature application, you might need superalloys to construct some of the equipment. Whereas if you can go to lower temperatures, you could potentially use lower cost materials. So that is an incentive to consider using a more expensive catalyst. Well, we did this whole comparison, and actually, before we get to the comparison, there's one more thing which we need to consider when switching from nickel to ruthenium, which is there are process constraints that come into play when you want to switch. So what you're seeing on the graph is essentially thermodynamics. So it shows ammonia conversion as a function of temperature at different pressures. So that's what the different colored lines are. Typically, ruthenium we see has a lower operating region compared to nickel. This also means that if you want to deliver hydrogen at high pressure with high conversion of ammonia, there's a challenge for ruthenium. You have to drop the temperature, you have to drop the pressure, to get the high conversions. The consequence of that is if you want to be still delivering 50 bar hydrogen, you need to have a post-cracking compressor. So that has to be taken into account when you do the comparison. The second challenge is actually the narrower operating range of ruthenium. So because you're using ruthenium, you need to be able to have good control of your whole reactor to make sure the conversion happens effectively. So we had to factor this in when considering the switch from nickel to ruthenium for comparative reasons. Is it cheaper? Is it not? I can already tell you, it is. So what we compared was what we called the marginal cost of ammonia cracking. So that excludes, let's say, the fuel use, but only sort of capex, the catalyst cost. And you see that ruthenium can have a 25% lower cost for ammonia cracking. But why does it have a lower cost? And essentially, it's the trade-off that I mentioned earlier with respect to the capex as well as the cost of ruthenium. So in this particular case, the materials are so much cheaper that it leads to a lower cost for ruthenium, but the cost driver also flips. So now the cost driver for ammonia cracking becomes the electricity as well as the catalyst. So this benefit you have is dependent also on the price of electricity that you have. So does this mean that we will always use ruthenium catalyst for future ammonia cracking projects? Unfortunately, it's never as simple as that. There's other commercial aspects that has to be taken into account. What I mentioned earlier was that ruthenium is a precious metal, and it's available currently in limited volumes. So what we did was we also looked at the total volume of ruthenium that is supplied to the chemical industry and compared that to what would be required if you want to make 100 kilotons of hydrogen per year, or if you want to make 5 million tons of hydrogen per year. And the bottom line here was, if you're going to even make 100 kilotons, that could have a significant impact on the ruthenium market that's out there. And if you want to make 5 million tons of hydrogen per year, that warps the current supply. So if you really want to have ruthenium as a serious large-scale solution for a catalyst for ammonia cracking, the recycling needs to be addressed or the loading needs to be significantly reduced. And the work still needs to go on to that. So our view is that for large-scale ammonia cracking, nickel might be better in terms of the availability, but there are still applications where ruthenium could play a role as a catalyst for ammonia cracking. Now, just wrapping up, in terms of what I just said, ruthenium can lead to a lower cost of ammonia cracking, or let's say lower marginal cost. And that's because the high cost of cracking can be offset by cheaper materials, as well as, you pay for that with higher electricity prices. And finally, the availability of ruthenium is likely to limit the wide-scale deployment and use of ruthenium for ammonia cracking. But of course, these are just two different aspects of ammonia cracking with ruthenium nickel. And there are many different aspects. And as Duiker, as a company, when we look for a client on what is required, we take these aspects into account. So if you would like to know a little bit more or have a copy of the presentation, please give us a call afterwards. We're also in booth B10, just right at the end over there. And also my colleague Albert Lanza is present there, so if you have any questions. So questions, I see, please. 1 second, I can't hear.
Hello, my name is Gilad from Katamon. And my question to you is, do you produce the catalytic system or do you buy it?
So the catalyst itself, for us, we procure that commercially from catalyst vendors. So we are catalytically agnostic. Thank you. Any questions? No? Okay, thank you very much.